In this video, we're going to talk about the application problems using rational equations. And in this type of application problems, we're going to focus on the idea of completing certain amount of work and how that's related to how we can use rational equations and expressions overall. And in this type of application problems, you will see the scenario will generally look like whether two individual subjects are working individually to complete a task, or these two are collaborating to complete the task together. And if we look at part A, or number 1, we can see in this scenario we have two pipes that are being used to fill a tank, and if pipe A alone is working, it'll fill out the tank 4.5 times as fast as pipe B does, and when both pipes are turned on, it takes 18 hours to fill out the tank. And we want to find out how long it would take pipe A to fill out the tank on its own, and what about for pipe B, how long it would take for it to completely fill the tank on its own. And when we are working with this type of scenario, we're going to base everything off the formula that if I want to complete the total amount of work, the work being completed is a product of rate times time. So rate is how fast, in this case, the tank is getting filled, and time is the amount it takes to fill the tank, or the time that elapsed as the process go on. And in this scenario, when we think about the work that's being done, whether the two pipes are working individually or when they're working together, we're just filling out one single tank. And that's an important thing to notice for this type of problem, because whether two subjects are working individually or together, they're always completing one single task. That task amount is going to be the same. In this case, it's filling the same tank. So essentially filling the same amount of volume in this case. And based off of this equation we're going to start defining the variable and also think about how we can use this equation to set up our new equation with a variable. So in this case, we want to find how long it would take pipe A to fill the tank and how long it would take pipe B to fill the tank. So in this case, because we know pipe A fill out the tank 4.5 times as fast as pipe B. So pipe B is a slower pipe by itself, and I'm going to set up the variable based on the slower one, just so I can be using a little bit easier operation, because I prefer multiplication to division. So I want to use B essentially as a baseline and reflect that pipe A's rate will be 4.5 times of pipe B. So based on this, I'm going to say that we can let the time it takes pipe B to fill out tank be we can call it T over here, BT hours. And I know to use hours as a time unit because that's what we're given in this case. So now once we have set up the variable, we want to kind of consider the different scenario. So if, let's say, pipe B is working by itself over here, it's filling out one single tank, so the work being done is 1, and we just set up the variable, so we know it takes the T hours for pipe B to completely fill the tank. And then to find the rate, because we have the relation that work is equal to rate times time, to find the rate, that relation still holds. So we can actually get, as a result, rate is equal to work divided by time. And if you need a little bit extra work to see how this gets out, if we want to get rate by itself, I can divide time on both sides. Once I do so, you can see time and time cancel out, and rate becomes work divided by time. So same thing, rate equals work divided by time. Work is 1, time is T over here. So we know the rate of B alone is 1 over T. And then let's look at A again over here. So in particular, I know that the work A is going to complete by itself is 1. And I also know pipe A can fill the tanks 4.5 times as fast as pipe B does. That means the rate of A is 4 times of B over here, or the rate of B. So it'll be 4.5 times 1 over T over here. You could go ahead and figure out the time over here again just by doing the division over here, and that also gives us some opportunity to simplify this expression altogether. So 4.5 actually you can convert into a fraction to be 9 over 2t over here. So this would be really 9 over 2t. And then for the time as a result, if you do 1 divided by this, it'll be the reciprocal of 9 over 2t, which would be 2t over 9. This information for time is optional. You will find out that later, but if you're ever unsure which piece of information will be useful, it doesn't hurt to follow the table throughout the whole process. And now if they're both working together, the total amount of work being done is still filling 1 tank. And we know the time it takes is 18 over here. And then we can see the rate. The rate will be 1 over 18 in this case. So the nice thing about us filling out the time is that now you have this relation of everything being in the table filled out over here. And what we want to focus on when two subjects are working together is we can actually relate their rates to each other. So the time is not necessarily going to change in this linear fashion. It doesn't directly give us a subtraction of time or addition of time, but when we think about the rate of how the work is being done, when these two pipes are working together, their rate basically is a sum of these two individual rates added together. Because of that relation, we can use the middle column, this rate column over here, to think about what is really going on. So in this case, I really have the scenario that the rate of B plus rate of A equals a rate of them working together. So in this, I would have 1 over t plus 9 over 2t, and that's equal to 1 over 18 in this case. So we're setting up the equation based on the rate. And in this case, to solve this equation, we want to use the knowledge we have about rational equations, and we want to use LCD here. The least common denominator in this case, for a constant, it would just be 18. For the variable, it'll be t over here. So now this is going to be a multiple of all the denominators we have. And I'm going to go ahead and multiply 18t to everything. And if it helps, you can write it as 18t over 1 over here. But otherwise, you can also just multiply each numerator by 18t and see how the cancellation works out. So here in the first term, t and t cancel each other out. Then we're left with 18. Second term, we have 18 and 2 cancel out, which leaves us a 9, and also t and t cancel each other out. So 9 times 9 will be 81. And lastly, 18 and 18 cancel out. So we're just left with the variable t. And to simplify, we get 99 is equal to t over here. Now if you remember what t represents the amount of time it would take B to complete, to fill out the tank over here. So we can say that right away it takes pipe B 99 hours to fill the tank on its own. And we're not done yet. We also want to find how much time it would take tank 8 to fill out the tank. And this is where you can use the expression for time directly. I know the time for A it takes is 2t over 9. So 2t over 9 in this case is equal to 2 times 99, which we just found, divided by 9 over here. And with a cancellation of a factor of 9, I have 2 times 11, which is equal to 22. So that means it would take 22 hours for pipe A to fill out the tank individually. And if you look at the relation between the time, you can see pipe B takes 4.5 times as long as pipe A as well, based on the fact that pipe A fill out 4.5 times as fast. So I hope this is not surprising as a result. And this is something you can look through your final answer and see whether everything still makes sense with a given information.